This is your heart, a complicated, amazing organ that beats around 100,000 times per day, pumping around 2,000 gallons of blood. Looking inside, notice that every beat of the heart looks the same. Same rhythm, same order. In this video, we'll learn how the heart coordinates its contraction, why that's so important, and how a diagnostic tool called the ECG can be used to measure if the heart is beating in order like it should. Let's do it. Every heartbeat should look pretty much the same. Atria contract first, helping fill the ventricles with blood, and the ventricles contract next, pumping blood out into the arteries. Atria first, ventricle second, every time. This order makes sure that the heart is pumping efficiently and in the right direction. But how does the heart know to contract in that order? Like everything in physiology, something's function is based on its structure. So to understand how the heart works, let's look more closely at how it's built. The heart has a layer of myocardium, or cardiac muscle, surrounding the atria and ventricles. The myocardium is made up of contractile cells, cells that will actually contract and relax to drive blood flow. But contractile cells can't contract on their own. They first need to be electrically stimulated or depolarized. Depolarization is just a fancy word for a cell getting more positive. The increase in positivity will stimulate the cardiac muscle cells, causing them to contract. The problem, though, is that cardiac muscle can't generate its own depolarization. We'll need some help. We need a second type of cell called autorhythmic cells. Autorhythmic cells are organized into a network. A cluster of autorhythmic cells in the right atrium, known as the sinoatrial or SA node, is connected to the atrioventricular or AV node, which leads into the bundle of His and eventually the Purkinje Fibers in the ventricles. Each of the cells in this network is capable of automatically and rhythmically firing an action potential, exciting the muscle cells around them to contract. But to coordinate our heartbeat, we need these autorhythmic cells to follow a very specific order. The autorhythmic cells in the SA node will start it off, automatically generating a depolarizing action potential. This electrical signal will then spread through the network using connections known as gap junctions, spreading from one autorhythmic cell to the next. But as it goes, notice that the electrical signal, shown in yellow, is also spreading out into the myocardium and the contractile cells. This excitation will then stimulate the atrial muscle to contract. The electrical signal continues to spread, reaching the AV node and then traveling down through the bundle of His and the Purkinje Fibers, stimulating and initiating contraction in the ventricles. So, a depolarizing signal is automatically generated in the SA node, which spreads down through the heart, generating muscle contraction as it goes. For that reason, I like to think of the heart like a firecracker. Firecrackers can't explode on their own. You have to light them first. To set off a firecracker, you light the fuse at the top, which then spreads down. But as the signal travels down, it also spreads out into the firecrackers, causing them to explode. This fuse that we lit is like the network of autorhythmic cells, generating and spreading a stimulating signal. The firecrackers are like the contractile cells, the ones that will actually explode or contract when they get stimulated. Looking back at our heart, when the autorhythmic cells in the SA node depolarize, this is like the fuse being lit. The signal then spreads down, stimulating the firecrackers or contractile cells along the way, causing them to contract. Notice though that since the heart's fuse gets lit at the top in the SA node, this forces the positive depolarization to spread from top to bottom, which gives the heart its natural order. Atria will contract first because they're closest to the SA node, ventricles will contract second. Once one cycle is complete, the SA node autorhythmic cells will fire another action potential, starting the process all over again. That's why the SA node is called the pacemaker. It determines the pace for how frequently our heart beats. But to make sure your heart is beating in this order, we can use an electrocardiogram or ECG. An ECG measures the electrical activity in the heart. For example, here's an ECG of a normal heartbeat. When the SA node depolarizes and the signal spreads through the atria, the ECG records a bump known as the P wave, which represents the atria depolarizing. After the signal passes through the atria and the atria get fully depolarized, the electrical signal pauses for a split second at the AV node, allowing the atria time to finish contracting. So So, on the ECG, we get a flat line known as the PR segment, representing no change in electrical activity. Once it's ready, the signal spreads down into the ventricles, generating the ECG's QRS complex. The QRS complex represents the ventricles depolarizing or getting stimulated, triggering them to contract. Once the ventricles are fully depolarized, they'll finish contracting without a change in electrical activity. That's why we see another flat line called the ST segment, representing no change or spread in electrical activity. Finally, to restart another cycle, we'll need to make the ventricles relax. The heart does that by repolarizing the ventricles, or making them negative again, which is recorded by the T wave on the ECG. The repolarization causes the ventricles to relax and gets them ready to contract again in the next heartbeat. Once one cycle is over, the SA node will fire again, initiating atrial depolarization, or the P wave, ventricular depolarization, or the QRS complex, and finally ventricular repolarization, or the T wave. So, our heart's rhythm and its order all comes down to a network of autorhythmic cells that help our heart beat like clockwork in the same way every time.